Hello, everyone.
Hello, hello. So my name's Amanda.
And my name's Karen. And we often do these types of presentations together, don't we, Mandy?
We do,
Yeah,
yes, yes. We work together quite a lot. So I think between us, we've been teaching for over 50 years, haven't we?
we have. It's scary when you say things like that.
it is. But I've earned every one of these grey hairs, I think. Terms of that. So we do. I was a head of science, deputy head, and head teacher, and now work in school improvement and do a lot of writing of resources, which you'll learn about later. And doing a lot of bespoke training and working with Karen. Karen, you introduce yourself.
Yes, so I've got over 20 years teaching experience. So that's everything from head of department up to assistant head, Senko. And like Mandy, write a lot of resources. But I also lead at Pixel, the education organisation, and I lead on science from 4 to 18 and on assessment for 11 to 18 at Pixel.
Excellent.
Hmm.
So we've got a poll before we sort of really get started, and what we'd like you to do is tell us from 1 to 10, on a scale of 1 to 10, how confident you feel about embedding disciplinary literacy into your science sessions.
Yeah.
So let's see where
And
we are.
10 being really, really confident and 1 being not very confident at all.
Yeah, cool. So we'll just give you a moment to do that.
I don't know if we are near the end of the voting there,
Okay.
whether we can see the result.
Oh, there
Oh,
we go. So let's have
excellent.
a look.
Okay,
Okay.
interesting.
So quite a variety. So that's great to see.
Yeah.
Um, so
Very interesting to see some of you are quite confident. So hopefully you still learn something from today. That's the important thing. So we're going to give you some
yeah,
different strategies that you can use in the classroom, some of which you may not have come across.
excellent.
Mm. Okay.
Right.
So we're going to start first of all thinking about a couple of quotes, aren't we, Mandy?
Yeah, yeah. These are
So the first one is from a chemistry paper, actually, but it's pointing out the fact that when we're thinking about science and we're thinking about literacy in science in particular, we need to think about the fact that we have got all these words and symbols that we've invented. And that we often only use in a science context. So, in a way, it's almost like we're teaching a modern foreign language. And that quote at the bottom there from Wellington and Osborne, if you're really interested in disciplinary literacy, and particularly in science, that Wellington and Osborne text is a really good place to start because I think that's fundamentally where a lot of the thinking behind disciplinary literacy and literacy in science has started. So, a couple of quotes thinking about the fact that we are making stuff up in science in order to explain the world around us. And I think that's really important.
yeah, and I think that word symbols in the top quote is important as well. Because we use
Yeah,
a lot of symbols, don't we?
we do, yes. And one of the issues we have with symbols actually is that, you can move from one science to another science and into maths, and those symbols can have different meanings
Mm,
in those different contexts, which makes it even more confusing for students.
absolutely.
But I think it's also a little bit more complicated than that because we have to if we're thinking about language in science, one of the first things we need to think about is that point that we are inventing words. So we're making words up. They do have a foundation, and we'll talk about that foundation in a second, but we are making up these words within science and we're using them within science. And quite often those words are only ever used in science. And if they are used outside and in real life, they may have a completely different meaning. And then to make it even more complicated, sometimes those words have a different meaning in different sciences. So if you think about the word field, for example, or species, field has a completely different meaning in biology to physics, and species has a different meaning in chemistry to biology. And then often words are used incorrectly in real life. So many of us would have heard people talking about learning by osmosis, for example, where people think they're using a word correctly in context, but clearly aren't. So those are, reasons why language in science can be difficult. On top of that, we've got English, students with English as an additional language. So that creates additional issues for those of you who've got large cohorts of English as an additional language. And this is a really interesting fact, actually, which I didn't realize, which is 80% of technical language within science, within engineering, etc., derives from Latin or Greek. Now, when my dad studied science, he was a microbiologist. When he studied science, he went to grammar school. And he learnt Latin because that's what you did when you went to grammar school. You learnt Latin alongside the science, which meant as he was learning these terms in science, he could see where the word had come from the Latin, and therefore had a better or a good understanding of that word. And of course, most students these days aren't studying Latin alongside the sciences, and that can complicate things as well. So even though these words have got that sensible bedding in a dead language so that we can connect those words together with similar meanings, etc. Students don't have that same familiarity with Latin as maybe previous cohorts of scientists have done. So maybe they don't see the logic as much as those previous scientists maybe would have done, which is quite interesting, isn't it, Mandy?
Yeah, it is. And there's those other words, isn't there, in science, like volume and amount, that we have to be
Mm,
really careful with that, if we're not really using our language accurately, we can fall into those traps. And so the students are picking those up as well and then get penalised on examinations as well, aren't there? There's a few of those, isn't there? Like big and large and little and small, and they're not good enough in
yeah.
science.
Yes, and that frustration sometimes that parents can have and students can have when they feel like they've written a wonderful answer, particularly in a subject like biology, where they feel like they've written the text and they feel like they've shown their understanding, but because the language hasn't been specific enough,
Mm.
they've not picked up the marks, and that gets increasingly more problematic as you get near A level. And of course, they're taught in subjects like English, for example, that it's okay to use synonyms. And we had a big debate in Pixel actually about synonyms because part of the English resources that were being produced for Pixel had, synonyms and homonyms and things like that in place. And we had to say, well, in science, we can't do that. Students need to use this specific technical language in the right way. And that can be frustrating for students as well when they're being taught in, other subject areas about, how all these different words have a very similar meaning and we can use them in the same context. We can't do that in science. We've got to be specific. We've got to be accurate. We've got to be precise with our language.
Absolutely.
Yeah.
And I think we don't often talk enough in departments about language and the correct use of words as well, do we? And so
Mm.
there might be non-specialists there that are using the terms which are not specific enough
Yeah.
in classrooms.
And I think that's where mark schemes, looking at mark schemes is beneficial because they're very specific about what language is needed. And that can really be used effectively to train the teacher. You need to be careful when using mark schemes with students. A lot of the examination reports that have come out recently have been saying over the last couple of years that there's evidence of students learning past mark schemes and regurgitating them as standardized answers, and they're not getting the marks because they're not linking it back to the question effectively because they've just regurgitated a previous mark scheme.
I think there was quite a backlash against a question on the exam paper this year on the biology, which is about osmosis. And students were asked to talk about what was going on with the potatoes, and they were talking about they are increasing in size, rather than talking about it at the cellular level, and so got no marks. But clearly they kind of understood what osmosis was and the concept and what was going on, but because they didn't use the cellular level, they didn't get any marks, and that was quite tricky.
Yeah. So yeah, about being really specific with that technical language.
Yeah. So let's have a think about this. So what are the barriers then to us developing literacy in science in our classrooms? What do you think some of the barriers are? I wonder if you could put in chat what you think stops some science teachers from doing this in class.
Yeah, time constraints is coming up a
Time's
lot, yeah.
coming up a lot. Out of the comfort zone.
Yeah.
Time. Not literacy teachers.
Yeah.
Too much content, etc.
It's good to
Yeah.
hear from the curriculum review that they've recognised there's too much content in science and history. So fingers crossed for that.
Let's hope. Yeah,
Yeah.
absolutely. Yeah, reading levels, etc.
Oh,
Cool.
Tracy, I like the fact that you was it Tracy? Sorry, Maria. I like the fact you called it the density of the curriculum. That's a nice way of putting it, actually. Yeah, not just the fact that it's overly full, but the fact it's quite dense as
Yeah,
well.
yeah.
That's quite an interesting terminology. Well done, you.
So
Mm.
we've done some research. Well, we didn't personally do it, but some research done about what science teachers are saying, and you've put loads of those here. So Karen, if you could flick
Yeah.
the main barriers, I think you've covered most of them. Time being the number one, but if we just think about it in a slightly different way. Surely time spent in doing a really good literacy activity is developing and deepening our, students' understanding of science. And it's probably tweaking, not actually doing an awful lot of spending an awful lot of time on that, but it's the tweaking. And then teacher of science and not a teacher of literacy, we hear quite a lot. But actually, if you look at the national curriculum, it does have an imperative to us of developing literacy in our subjects. And it kind of links with the next one. It's the English's department role to develop literacy. Now, I come from a time when there was a big push on literacy and numeracy,
National
and
strategies, weren't they? Mm.
there was a literacy lead across the school, and fairly typically the literacy leads always came from English, and they were doing whole school activities. And for me as a scientist, I always found it quite difficult because they weren't really translating as easily to my subject. I'm the expert in science in my classroom. I'm the expert, so it's me taking the time to develop that in my own scientific literacy within my classroom, surely. And obviously, in our examinations, we've got that role of extended writing in there. So we need to give those opportunities. As long as they can read the exam questions, what's the issue? Well, I would answer that one and say that reading the question obviously is very important, and if they can't do that, that is an issue. But they need to know what the exam question is actually asking them to do. And so for us, as science teachers, it's being able to decode that, what the question actually is asking as well in terms of that literacy. I noticed a few people there were talking about reading ages and getting students to read, and I think it's important to keep trying and not do the I tend not to ask them bit. It's thinking about what it is you're asking them to read and inspire and challenge and all sorts. I think Karen often tells a story about magazine articles and boys in terms of getting their reading, and if you can get those science
Yeah, when I was a Senko, I went and visited. You go out and visit year sixes before they come up, and the year six teacher and the parents were there with the child, and they were absolutely adamant that he didn't read. That he didn't read and he didn't write, and they couldn't get him to read and they couldn't get him to write. And he was a very, very reluctant reader, very, very reluctant writer. So I sat next to him and I said, "Do you like Minecraft?" And he said yes. And I said, "Have you got any books on Minecraft?" And he said yes. And I said, "Do you read blog posts on Minecraft?" He said yes. And so we talked about the fact that that was reading, and that it didn't have to be, it's about, there's lots of different things that you can read and lots of different contexts that you can do reading in. And we actually got him to write stories about YouTube videos that he'd been watching about people playing Minecraft. So he was able to latch that onto that as an entry point. And I think that's, making the what they're reading of interest actually makes a difference as well as reading for meaning. So reading for pleasure mixed in with reading for meaning.
Yeah, yeah, absolutely. And surely, going back to the bullet point, surely giving the keywords is enough. I think when we talk about literacy, I think our natural bent is to immediately go into the keywords and talk about what they are and make sure that the students know what they mean and so on, and breaking them down into their etymology. And yeah, that's important, but they need to be able to use those keywords in a sentence, in a paragraph, in a bit of extended text, and linking ideas together. So keywords is not just enough. They're important bricks, but we need the word, the sentence, the paragraph level in terms of that.
And the EEF is very, very clear on that in terms of literacy, isn't it? That we
Yeah.
should be doing that.
Yeah, and then the last one is, the literacy. We only really focus on literacy when we're working with high attainers. We're only really being specific about, them using the right terms, which is quite sad, really, isn't it, to think, because everybody needs this support in their literacy. They're less likely to pick up the skills if you just give them the same types of task as well. So it's trying to look at different ways, and we're going to show you a few of those as we go on. So hopefully that answers some of the barriers there. Because you might have to talk to other people, in your career about how to develop literacy and overcome those barriers. So.
And one of the things that's quite interesting when we were doing some research around disciplinary literacy is the fact that science texts are what we call multimodal. So that means that in science, we transfer knowledge and understanding through not just words. Which is, when you read in science, you've got to be able to read an equation, read tables, read diagrams. If you think about this blood circulation, for example, and how much meaning is conveyed in a diagram showing the circulation of blood around the body, the use of color, the use of the way it's labeled, it shows the whole journey and the direction of the blood around the body. And then you can have conversations about what's happening in all the different organs, etc. So there's a lot of information conveyed that way. And so science alongside maths is multimodal. So when we teach students to read in science, we have to teach them to read graphs, to read the numbers, to read equations, to read diagrams, to read data, as well as words. And so we need to make sure that we are decoding these as well as decoding texts. The actual terms and the words and the paragraphs. So it's very complicated for us in science. And actually in Pixel, we've taken a route where we've got a general disciplinary literacy strategy, but alongside that, we have a science strand and a math strand as well, because they're multimodal and we need this additional support as well. So we're going to have a look at an example. So if we place this equation up on the screen now, what I'd like you to do is think about if you were writing that, physically writing that up on the board in front of a year 8 class, for example. You just done, you just burnt some magnesium and oxygen and you were putting that equation up on the board. Think about, as you were writing it, what would you actually say? What would you say when you're reading that equation to a year 8 student? And then think about how that might be different to if you were reading it to a foundation GCSE student. And then if you were reading it to a higher tier foundation student, and what the differences might be. So if I just give you a moment to think about that, and maybe write in chat how you would read, what would you actually say as you read that aloud to the students? So a couple of ideas in chat would be great. If I can get the chat up. Yeah.
I think Elaine's just said use a word equation.
Oh, absolutely. Yes. Particularly at Key Stage 3. Yes. Yeah. But imagine the word equations up there and you're reading this. Yes. So including the state symbols. Absolutely. The fact it's forming a compound. Yeah. So introducing terminology like that. Oh, nice. Yeah, circles and dots to show the molecules. There's something called Johnson's triangle, which is worth thinking about when you're teaching about symbols in science, which is about making connections between what you can see and experience, representations like this, and then thinking about the particle model, and thinking about what's actually happening to the particles during the chemical reaction. Yeah, so at key stage three, you would be talking about in terms of the elements, wouldn't you? Magnesium, oxygen, and then the compound magnesium oxide. Two lots of, yeah. Yes, so explaining that magnesium's got the symbol Mg, yeah. So Claire, feeling very strongly that you would do the same at each level. I think when you see the sentence I put up, you might change your mind on that. But yes, the arrow, focusing on that arrow. How many
Yeah.
times do students say equals when they look at that? Yeah. So if I just pop up, this is what I would say to a year 11 higher tier student as I was reading. Whoops, come on up. There we go. So 2 moles of solid magnesium react with 1 mole of gaseous or gaseous oxygen to form 2 moles of solid magnesium oxide. Now that's what I'd say to a top end year 11 group. If I was talking to a foundation tier group, I would not mention moles for obvious reasons because they don't need to worry about that. And if I was talking at key stage three, I might even not include the state symbols during the discussion. And we might be talking, some people were talking about 2 lots of and things like that. Um, so I was explaining at a training event recently to a group of senior leaders who weren't scientists about the fact that you can have a symbol equation like that you would read differently depending on your audience. And there isn't anything, if you're reading a paragraph of text to a group of people, you would read it the same way if you were reading out loud. But reading out loud, that equation is different depending on your audience, which adds complications. I'm going to pop up a simpler one here. Uh, how would you read that one aloud? Imagine you were doing something similar to the one I've just done above. How would you read that? Yep. So what would your words be? Imagine you were writing a sentence like the one I've written above. Yeah. Excellent. I'm seeing a word there which we need to talk about.
What? Ah, they're falling into the trap,
Fallen into my
Karen.
trap.
Oh,
Marvelous.
dear.
We didn't know about this trap, did we, Mandy? Until about
We fell into it as well.
we fell into the trap as well. Okay.
I
We're all
think
we're having a go at the
most
math.
teachers would
Go on.
say most teachers would actually say F equals MA though, wouldn't they?
Yes, they would. Most
I
teachers,
think,
as they're writing it on the board. Yeah.
yeah,
Yeah.
yeah, which doesn't help much.
Yes, which is what I would have done. If I
Yeah,
genuinely thought about it, I would write F equals MA, and then I'd
yeah,
explain what the F stands for, the M stands for, and the A stands for afterwards. Rather than reading it and
yeah.
saying this, she says, there we go. Resultant force. We've been told quite forcefully by some physicists, haven't we, Mandy, that it's
We have
resultant force and
indeed.
not force. So resultant force equals mass multiplied by acceleration, not times by, but multiplied by. And this is where we should be supporting our maths department. We quite often ask our maths department to support us. We need to support the maths department as well and make it really clear that it's multiplication, not times by. And I fell into the times trap as well. In fact, both of us did until we did some research and collaborated with our maths colleagues on this. But what we're assuming, there's some assumed knowledge there, is we're assuming, and they do in maths as well, that students understand that when the M and the A are next to each other, they're multiplied by each other. And it's really important that when we're writing up equations like this, we are saying it in words, not in letters. So we're making it really clear that the mass is multiplied by the acceleration, and we're not just saying MA. That's the point we were trying to make there. But yeah, it's quite interesting when you start actually getting down into it, isn't it, Mandy, and thinking about how do I actually go about reading this? And it's the same with tables, it's the same with graphs, it's the same with diagrams. Consciously thinking about how am I going to read this aloud in words to explain it so that students really understand what's going on in terms of those symbols. And I think we forget sometimes. And I certainly did during my teaching practice. So
Absolutely, and it's going back to that original slide about the symbols that we use in science, and the fact that they can mean different things in, even in uh, even in science, they can mean different things,
yeah, I think the letter C's got multiple meanings, isn't it? The
Absolutely.
lowercase c,
Yeah,
it's all over
yeah,
the place.
yeah,
So depending on what it's in. Um,
absolutely.
okay, so that's kind of the research and the thinking behind it. And what we want to spend the rest of the presentation talking about are a number of different strategies that you can use in the classroom. And as Mandy said earlier, this isn't about doing more, it's about tweaking your current practice. So when you're doing retrieval practice, for example, at the start of lessons, when you're doing formative assessment during lessons, tweaking those activities into disciplinary literacy activities means you're not only supporting that acquisition of knowledge or recall of knowledge or application of knowledge, you're also supporting the literacy alongside that. And it's possible to do both just by tweaking the activities that you do. So we're going to introduce you to a few of them.
So because but so, or sometimes it's but because so, depending depending on where you look. This is a technique that was developed by Judith Hockman, and she calls it a sentence expanding technique, is what she calls it. So some of you might have come across it, but basically, if you go on to the next one, Karen.
Yeah.
It's a kernel sentence, and that means the sentence is the same, and then you put because after it, but after it, or so after it. So I might put plants need sunlight because plants need sunlight, but plants need sunlight so. And you can see that the because is a reason, the but is a contrasting idea, and the so is a consequence. And actually, it really makes students think quite hard. And what is quite nice is that you'll get lots and lots of different answers. There is no necessarily right answer to any of these, but all you're asking them to do is create sentences and think about their learning. So if we go on to the next one, here's a couple of examples. So, a moon orbits a planet, and you can see because, but, so. So you've got to complete those. The important thing in doing something like this is to make sure that the kernel sentence, the bit in bold there, is the same, so that students are thinking about the same concept at the time. And I think we've got another example there, which is about igneous rocks. They're just the other way around. So extrusive igneous rock cool quickly, but intrusive igneous rock cool slowly. And you can see the other two examples there. But you can see that students are really having to think about those as they do it. You can't do it for everything, but you can do it as a sort of an end of lesson, or a bit, a recall at the beginning of lesson, that sort of thing. But it also lets you see how deep their understanding is. The danger is thinking about the vocabulary, as I've put there. Think about, do they know the vocabulary to be able to use? But this is a really good way of making them, use connectives, because, but, and so, which is important for extended writing in terms of that.
It's also really good because one of the examination boards has made it clear that students really struggle with that concept of comparing, don't they?
Yes.
And contrasting different things and making those comparisons, and adding in these connectives really helps support that process as well. And as Mandy said, the vocabulary is really important. So what you may want to do when you've given students a task like this is provide some vocabulary that you'd like to see in the responses afterwards, and in these completed sentences as well. Yeah. Another example, which has been around for quite a long time, is concept mapping. And this is where you take two terms and you ask students to form a sentence within those two terms. So we've got an example here of oxygen and photosynthesis. And they really, what you're doing here is forming sentences. So as the EEF said, it is important for them to understand these keywords, but they need to use them to form sentences. So here's a very simple concept map where you've just provided two terms, but in actual fact, what you want to do is provide a whole series of words and ask students to make direct links between the terms. And some of those words will be easier for students to make links with than others. But it's all kind of important and linked together. So we've got introduced words there like limestone and plastics to try and get them to link together outside of photosynthesis into some of the other learning that they might have experienced. And this is an example of a low threshold, high ceiling task. So this is where students should be able to access it at a low level. So they should be able to link together a couple of words into a sentence. But those higher flyers can link multiple words together into sentences. And you could ask students to try and see if they can make a sentence with four of those terms in, for example, to link together those concepts. So concept mapping, if you Google concept mapping, you get quite a lot of different ways of doing it, but this is probably the easiest. And often we're worried about time, as was mentioned in lessons, and this is something that can be supported during tutor time, for example, is providing keywords during tutor time if you've got literacy activities going on in tutor time, and students actually creating these links while they're there, in outside of science lessons. And it's very easy to provide slides with key terms on, and maybe even a couple of examples to help support them with the learning, just to help them form sentences from keywords.
And I think another way of increasing the challenge of this, you've got all of those words, and sometimes you can say, right, how many can you connect sensibly within 3 minutes? We did this, didn't we, with a group of teachers? It was quite interesting to see what came up and how many of them managed to get them all linked
Yeah, I
together.
was going to say getting them all, that's the real challenge, is can you create sentences that uses all of those words, which is about, linked back to, I mean, this is obviously linked to carbon chemistry. So,
Yeah.
yeah.
But once you've done all of that, you can then use that to write a paragraph as well, can't you?
Yeah. Yeah, so if you had a six marker, for example, and you knew the keywords that you wanted students to use in that six marker, and you just provided the keywords and asked them to link them into sentences and then work on linking them into paragraphs, you've got an answer to a 6 mark question. It's just a different way of approaching it.
Yeah. Here's another way. So modeling, basically, what does a good one look like? So here we've got a description about alpha radiation. It's a helium nucleus containing 2 protons, 2 neutrons, can't speak today, is the most ionizing. We've got a nice little graphic there that goes with it. And we ask the students to do similar for beta and gamma radiation following that particular sort of style. So they're safe in the structure, they know what the structure is, and they just need to basically tell you what beta and gamma radiation is doing that. So it's quite a nice, very simple, and actually, as you go through it, you could be showing them the picture as well, and talking about what the different colours of balls are, that's on there. So copying the sentence style, that's an easy one to do.
Yeah. So now we've got a whole series of other examples which we produced for Collins. We're going to do them at word level, then sentence level, then paragraph level, and then reading and comprehension, so that you can see the differences between them. So we're going to start at the word level first of all.
So if we look at this, Karen alluded earlier to the circulatory system, and how often do we ask them to label these? And they're labelled, and we don't really do much with them. But this one, it's got inherent clues in it to help them. And if you sort of show them this, so the word pulmonary means to do with the lungs. In Latin, an atrium means the first room entered, and ventricle means a large chamber or compartment. And then you've got various clues within the picture, like artery, vein, right and left as well. And then asking them to actually label that. So students find it hard to label diagrams, and actually some of the exam boards are sort of saying they can't label basic diagrams. So that's quite a nice one. We're using the words in the context, basically.
Yeah. And what it's turned it into is a problem solving activity rather than a recall activity, because they can use the information in the text to answer the question.
And then you can build upon that like you would do probably in your normal lesson. Once they've done that, you can talk about the pathway through the circulatory system and ask them to talk to each other about the pathway of a red blood cell, using their diagram or trace it with their fingers and things like that.
Mm. This one's from physics. Now, this is a gap fill exercise, and quite often we have a perception that gap filling exercises are low level and are for, those things we're trying to remove from our teaching because they're seen as not useful. But actually, if you look at that paragraph there, it's actually higher levels of understanding are required to answer that. And actually, A-level sciences have some quite good fill the gaps activities in examination papers, actually, quite high level. So a fill the gaps activity can be very challenging for students to complete, and they need to show their understanding to be able to do it. And if we use the words that we're trying to put into the gap fill, if they're words that are commonly forgotten by students or misused by students, then it's a very effective activity to do. It's not effective when we pick random words to pop in there. We really have to think about the choice of words that we're actually putting into a gap fill activity. So that's an example from physics, quite a tough one, I would say.
It is quite tough. I
Mm.
tried to do that. It was quite tough, that one. And what I like about it, it hasn't got the begin the A or whatever,
Yes.
which basically just becomes a, ooh, let's see what fits,
Yeah.
rather than using your scientific knowledge in there,
Yeah.
which is quite good. And the next one, I love this one.
Yeah.
So this is about accurate terminology, basically. And so we've got a table there and some statements, and it asks you, is the term in bold used correctly? So you say yes or no. And if you are saying no, it's not been used correctly, you've got to select one from the words at the bottom. And there are some red herrings in there, at the bottom. They've got to use the right one. So coronary heart disease is caused by fatty material narrowing the pulmonary arteries. Obviously, that's a no. And the term should be coronary arteries. So it's helping them, to really understand what's going on there. I like the next one because it's
Yeah. It's a
common.
good one. Yeah.
Stents are used to reduce blood cholesterol levels, but obviously it's statins, but they're getting two things mixed up there, and they think, oh yeah, I've heard of that before. That might be. And the next one, this is what people, might generally say: tumor cells can be dangerous and spread to different regions of the body. But the answer is no. It's malignant. Tumor cells can be malignant and spread to different regions of the body. So it's really looking for accurate terminology and deeper understanding, in terms of that.
Yeah, and that's relatively easy to do. You don't have to have it in a fancy table like that. You've just got to think about what common errors might a student make when writing a sentence, what terminology might they use incorrectly in a sentence, put it in the sentence and ask them to correct it.
Mm, mm,
So that was word level. Now we're thinking about sentence level. So we're using key terms to form sentences here, and we've got a few examples. So a nice one to do is about generating definitions. So students struggle to understand the difference between oxidation and reduction in terms of electrons. And what's happened here is the definitions have been broken down. So you've got four different sentences there, and they've basically got to select so we'd start with oxidation is, and then we need to choose the correct next part of the sentence from B. C is always the same, oxygen ore. Then you choose something from D and then end up with electrons. And this gets them really thinking about what is the difference between oxidation and reduction, because parts of the definition are the same. C and E is the same, but B and D is different, and getting them to formulate that definition from that with the clues in the paragraph at the top talking about oil rig, just to help support them with that.
mm, It really unpicks that oil rig, doesn't it? And
Yeah,
helps understand that.
helps them understand it. So it's not getting them to do it in isolation. There are hints and tips and clues and that kind of thing as well. And then we've got another example of because but so, this time put into context. So and linked to a change in mass during a reaction. So this is an example where it can be embedded into practical work. One of the feedback from the examination boards this summer and previous summers is about students and not fully understanding practical work. So here we're using a buzz because but so in that practical context, which helps too.
And this one is helping us to unpack those two words, describe and explain, that students have such a lot of difficulty with. And, you know, present company accepted, quite a few teachers also have a problem with describe and explain. So it tells you at the top what a describe and an explain is, and how to answer it. And so it's asking you to describe the appearance of the root hair cell, but it tells you we want you to talk about shape, the cell wall, vacuoles and organelles. Okay, so we're giving those clues, and obviously these are scaffolds, and over time you would remove scaffolds. And then we've got explain. So explain how a root hair cell is adapted to take in water and minerals from the soil. Use your observations from part A, your description, and convert them into an explanation by adding words like so, or so that, or because. And it gives an example. The cell wall is very thin, so that. And it's doing something with the picture.
And it's helping them. You can imagine if they had a 6 marker which said explain how root cell hair is adapted. In order to answer that, they've got to have that beginning kernel of a description linked to the explanation, haven't they? And this is helping support them with answering that type of 6-mark question, as well as differentiating between the difference between describe and explain, isn't it?
Yeah, yeah, that's right. And then we've got how many times have we all done in biology, you know, what's the difference between an animal cell and a plant cell, or eukaryotic and prokaryotic cell? And we do the table of differences and similarities. Well, this one starts off like that. So look at the diagrams, design a table, complete a comparison. But then it asks you to do something with that table. So you've actively got to engage mind and write a sentence now about similarities, and then the next one obviously is about differences, and then you can see how it's building to an explain question underneath. So choose one difference between the cells and explain why this is necessary. And it gives you a little scaffolded structure there to help them get started. For those students that really struggle to put pen to paper on a blank space, there's a scaffold there to get them started. But we're doing something with those differences and similarities, rather than just creating a table and moving on.
Yeah, and this is what we're talking about when we're saying about tweaking activities rather than adding more activities to what you're doing. So just by tweaking that comparison table into something different means it's helping them with their literacy as well as their understanding of plant and animal cells.
It's all deepening that understanding.
Yeah. So next is paragraph level. So getting those, 4, 5, 6-mark questions and understanding how to formulate sentences. So we've got a few activities here that can help support with that.
So the first one, it's about contraception. You probably can't read it on the slide, but it tells you quite a bit at the top about different types of contraception. It sets a scenario about a couple that decide they don't want children, but want to keep the option open. And then you've got to evaluate the types of contraception that are available to them. And it suggests you use a table, so reasons why and reasons against, and it gives you some figures as well for effectiveness. And so they have to think about the pros and cons of each method in terms of that. And then the last one, which is the bit that they always forget with the evaluation, they've done the pros, they've done the cons, but then they don't make a judgment. Okay, so that's where the scenario comes important. So now write a paragraph to say which methods are most suitable for the couple in the question and explain why. And use the connective because and however in your answer. And so, you're really thinking about those contraception, and you've done this activity beforehand to prepare them, so they know about contraception. They know which one's going to be most effective, and why they would use it. And now they can feel they can actually put some sentences together in a paragraph in an organised way.
So yeah, so it's basically providing a scaffold, isn't it, to enable them to answer a 6-mark question on contraceptive.
Yeah,
Mm.
yeah. And then we've got very similar in terms of ecology and quadrats. So, but it's really focused now on the required practical in the English curriculum, which is linked to calculating the abundance of dandelions or whatever in a particular region. But it structures it in such a way that it chunks the answer. So first of all, we're thinking about how we're going to set it up. And we've got to use the terms quadrat, random, bias, and area in your answer. It gives you the units, meters squared, so helps them with that. Then next, decide how many times we're going to put the quadrat down. So it's making them think a little bit more about that. So I've got to use quadrat and count in there. And then finally, they actually explain how to use they need to explain how to find the mean number. Oh, it's buttercups, not dandelions, in the quadrat, and work it out. And it tells you to use mean and total in their answer. So it's just helping them to, structure that extended answer question for a common required practical, but it's got keywords in there to help them.
Mm. And then something very similar for, I mean, whenever this comes up, students struggle because quite often they will introduce a new chemical and then it throws students in terms of, formulating dry crystals of a different substance, and it throws them. But again, this asks them to, it explains to them what they need to do in the first bit of the method, in the next bit of the method, in the next bit of the method as scaffolding. To help support with that, but we're giving those key terms as well to help with that. So if you've got students who are leaving 6-mark questions blank, particularly related to practical work, providing this level of scaffolding, which you can do as a what's the word I'm thinking of, Mandy? Structure strip. That's it. In a structure strip style, or in a broken down question style like this, can really help support students with their answer. And if you have a look at the first question there, in that last one, which says read through the text and highlight 6 scientific terms, check with your teacher if there are any terms you do not understand. So that's asking them to engage with the text and the reading, because quite often students will jump down to the question and ignore the text or ignore the diagram that comes before the question. And that happens in examination papers as well. It's been shown that that's what students often do when they're reading. So it forcing them to go back and read text effectively.
Mm. Yeah.
And then, of course, well, this links so nicely onto the next level, almost like we planned it. So that idea or concept of reading comprehension. So that reading for meaning, understanding and decoding the text. We've got some examples of how you might support with that here as well. So here again, there's an example of first question, asking them to engage with the text. So not just reading the text, but explaining what they're looking for in the text, why they're reading the text. So, read through the text and highlight data for 2010, 2020, 2022, 2023 using different colours. So they're actually engaging with what's going on in that text. It's forcing them to read it and absorb the information and engage with that text. So that's the first thing that's important to do. So if you're giving any reading or reading comprehension, give that first question as something that forces them to engage with the text, not a question that just asks them for a fact or a piece of information from the text. This is another example. So this is about the use of wildlife corridors. And again, it's got that task to engage with the text at the top. So highlighting those scientific terms and checking for understanding. But underneath, rather than asking what are wildlife corridors, is asking why they're important. So it's asking them to think, right, okay, well, I need to know what a wildlife corridor is first of all, and then I need to think about why that might be important in an ecological context. So it's leveling up the question. So again, reading comprehension questions can be quite low level if you're not careful, where you're just extracting a piece of information from the text, a fact from the text, for example. Whereas this is taking it that little bit further. It's forcing them to really think about why that's such an important concept within, when we're thinking about biodiversity, for example. So examples of how you might support reading comprehension.
Yeah, because I think what students do when you say, you know, wildlife corridor, they go up to the reading and they'll go highlight wildlife corridor, and then they'll literally just copy out what that sentence says
Mm,
if you're not careful. It's really that why is so important there. It's really good. I've even seen teachers, who actually, do underline words for them, and so literally they're the words they need to answer the questions underneath. But
mm,
actually, that's perhaps not helping them to decode what's going on in there because it's taking it out of context.
mm. Now, you can obviously produce any of these types of activities yourselves, but Collins have very, very intuitively produced a pack, a resource pack of these types of activities that covers the whole of the AQA curriculum. Now, we say AQA because it's relatively tightly tied to AQA. However, it does work for other examination boards as well because there's a lot of crossover between the exam
Yeah,
boards. So the activities you will find will be useful no matter what examination board you do. So if you're interested in that,
460 pages of amazing stuff.
yes,
Activities for every topic. It's
yeah.
also got diagnostic assessments, hasn't it,
Mm.
as well, in there. So we've
And
got
it covers working scientifically as well at the start, which is
yes,
also an
yes,
area. And that was raised, actually has been raised for a number of years now about students' inability to use working scientifically terminology correctly. So
yeah,
accuracy and precision, for example, resolution,
yeah.
and terms like that. So that's all covered
It's
in there
also
as
got
well.
some current issues, hasn't it? Like air pollution,
Mm.
biodiversity, climate change. And misinformation, tackling misinformation,
Oh
I
yeah.
think it's called.
Yeah.
Yeah, in terms of pandemics, all sorts of things at the beginning as well.
Yeah.
So,
Very useful.
yeah, I think it is. I think Lee
Mm.
just said it really is an excellent resource.
It took
Dear.
a lot of work, I'll say that, say
It
that
did
much.
take a lot of work,
The amount of
but
thinking that went into that was quite
yeah,
high level.
but
So what we'd love to do now is we'd love for you to complete that same poll that you did at the start to see how confident you are now with disciplinary literacy. So if we're able to do that poll, and again, so 1 for not very confident at all, 10 for confident, that would be really helpful from our perspective and hopefully from your perspective. So hopefully you found that useful. We're open to question and answers if you would like to do that as well. Or reflections on anything that you might want to do differently as a result of this session would be really useful if you pop those in chat too. So once you've done the poll for us, that would be amazing. If we could have some feedback in chat, that would be great
yes,
too.
takeaway. What are your takeaways,
Oh
basically?
my goodness me, look at
That.
that. Well, that's
That's good.
marvelous. Thank you very much.
That's brilliant.
Yeah,
That's really good.
that's
So it really is tweak to transform rather than
treat to transform. Where did you get that from? Amazing.
say that, tweak to transform.
That's our new that's our
Dear.
that's our new phrase.
Tweak to transform. There we go.
Oh, no worry, Jane. No worry at all. Yeah. Thank you so much.
Thank you, Lee.
Thank you. So hopefully that was really helpful. Hopefully, if you're interested in buying the text, please feel free to do so. If you want to produce your own resources and share with people, feel free to do that too. But thank you very much for joining us and hope you found that useful. Oh, thank you very much, Evelyn. Truly useful.
A
Amazing.
question in the
Thank you.
Q&A.
Thank you very much. Yeah,
Um,
any questions, let us know.
so what's the difference of
Mm.
formative assessment from summative assessment?
So formative assessment you do as you're going along, as you're teaching, and you would normally respond in the moment. So you would say if you're doing mini whiteboards or something like that in the classroom, and then you would be able to see immediately how the students are doing, and you would be able to respond immediately. Summative will happen after all the teaching has occurred, and you will generally mark that outside of the classroom. And you can still do formative feedback from that summative assessment, but it will happen after all of the teaching, and it's usually used as some type of judgment on how effective that teaching was, I would say.
Well answered. I agree.
Yes, I think that easy tweaks, I think, is key, Tracy. Yes, thank you very much. Thank you.
Cool. Okay.
I'm going to stop sharing now. Do we have anything else we needed to say?
Nothing else in the questions.
No. So thank you very much for joining us. I mean, feel free to leave us if that's been helpful, but thank you very much.